Namaste everyone, welcome back to coinslive. In this video, we are going to solve LeetCode problem number 769, max chunks to make sorted. This is a medium level array problem, but the final solution is surprisingly simple. We will first understand the problem, explore the main intuition, implement the Python solution, perform a complete dry run, and finally discuss the time and space complexity. Let's begin. We are given an integer array called ARR. This array is a permutation of integers from 0 to n minus 1. A permutation means that every number from 0 to n minus 1 appears exactly once. We need to divide this array into some chunks. We will sort every chunk individually, then concatenate all the sorted chunks. After concatenating them, the complete array should become sorted. Our task is to return the maximum number of chunks that we can create. Let's understand this with an example. 10234. We can divide it like this: 1, 0, 2, 3 and 4. Now sort every chunk separately. The first chunk will be 0, 1. The second chunk will be 2, 3, 4. The remaining chunks already contain only one element, so they remain unchanged. After joining all the sorted chunks, we get 0, 1, 2, 3, 4. This is the complete sorted array. Therefore, we can create 4 chunks and the answer is 4. The important question is, how do we decide where one chunk should end? Because the given array is permutation of numbers from 0 to n minus 1, its completely sorted form is always 0, 1, 2, 3 and so on till n minus 1. This property is extremely important. At index 0, the sorted array should contain 0. At index 1, it should contain 1. At index 2, it should contain 2 and so on. Now, suppose we are standing at some element I. The prefix of index 0 to index I contains I plus 1 elements. For this prefix to become an independent chunk, it must contain exactly the elements that belong in positions 0 to I. Those elements are 0, 1, 2 and so on till I. So we need to determine whether the current prefix contains exactly these values. While moving from left to right, we maintain the maximum value that we have seen so far. Let's call it max so far. So whenever max so far will equal to current index, we can we can end a chunk at the current index. Why? Because if the maximum value in a prefix ending at index I is equal to I, then every value in that prefix must be between 0 and I. The prefix contains exactly I plus 1 distinct elements because the array is a permutation. There are also exactly I plus 1 possible values between 0 and I. Therefore, that prefix must contain 0, 1, 2 and so on till I. Once we sort this prefix, all these elements will move to their correct positions. Therefore, this prefix can form an independent chunk. That gives us a complete rule. Whenever the maximum value seen so far becomes equal to the current index, we have found a valid chunk boundary. Let's apply this idea to the example. Initially, chunks equal to 0 and max so far is 0. We begin traversing the array at index 0. The value is 1. The maximum value seen so far becomes 1. Now compare the maximum with the current index. Current index is 0 and max so far is 1. so they are not equal, so we cannot end a chunk here. This makes sense because the current prefix contains only 1, but the value 1 belongs at index 1. Its correct position lies outside the current prefix. Therefore, this prefix cannot be sorted independently. Now move to index 1. The value is 0. The maximum value seen so far remains same. Now max so far is equal to index because 1 is equal to 1. So we can end a chunk here. Our first chunk is 1 comma 0, right? After sorting we get 0 comma 1. These are exactly the correct values for indices 0 and 1. So we increase the chunk count to 1. Now move to index 2. The value is 2. The maximum becomes 2. The maximum is equal to the current index. So we can create another chunk 2. The chunk count becomes 2. At index 3, the value is 3. The maximum becomes 3. Again, the maximum is equal to the index. So we create another chunk. The chunk count becomes 3. At index 4, the value is 4. The maximum becomes 4. The maximum becomes 4 and the maximum is equal to the index. So we create the final chunk, that is 4. The chunk count becomes 4. The final chunks are these 0, 1, 2, 3, 4. Now second example, at index 0 the value is 4. So max so far will be 4, but current index is 0. They are not equal. At index 1 the value is 3. The maximum remains 4. The current index is 1, so they are not still equal. At index 2 the value is 2, so the maximum remains 4. It is not equal to index 2. At index 3 the maximum remains 4. It is not equal to index 3. Finally at index 4 max so far will be 4 and index is 4. Now they are equal, so we can end one chunk containing the entire array. After sorting the complete chunk we get this. Therefore the answer will be 1. We cannot divide the array earlier because the value 4 which belongs at the last index appears at the beginning. Any chunk containing 4 must extend until index 4. So why are we maximizing the number of chunks? Every time we find a valid boundary, we immediately end the current chunk. This gives us the maximum possible number of chunks. Suppose the prefix ending at index I already contains exactly the elements from 0 to I. There is no reason to merge this valid chunk with the next part of the array. Merging it would only reduce the number of chunks. Therefore, ending a chunk at every valid boundary produces the maximum number of chunks. Let's now write the pseudocode. So this is our pseudocode. We will initialize chunks as 0 and max so far as 0. And for every index and value in the array, we will update max so far with the maximum of max so far and the current value. If max so far is equal to the current index, we will increase the chunks by 1 and we will return the chunks. That is the entire algorithm. We only need one traversal of the array. Let's write the code and implement the solution. We initialize chunks equal to 0. The variable will store the total number of valid chunks. Then max so far equal to 0. This variable stores the maximum element encountered during the traversal. Now we will traverse the array using enumerate. The index value stores the current index and the value stores the element at that index. Inside the loop, we updating the running maximum, max so far, and the maximum of max so far and value. Then we will check the whether the running maximum is equal to the current index or not. If equal, then we will increase the chunks by 1. If this condition is true, the current prefix contains exactly the elements needed for the corresponding sorted positions. Therefore, we have found a valid chunk boundary. We will increase the chunk count. Finally, after processing the entire array, we will return the number of chunks. Let's do a complete dry run. The first iteration, the current index is 0 and the value is 1, and max so far will be 0 and 1, and the max is 1, so max so far will contain 1. Now check whether 1 is equal to 0 because index is 0. That's why this is false, and chunks will be 0. We will not increase, and we do not end a chunk here. Iteration 2, index is 1, current value is 0. Update the maximum, max of 1 comma 0 will be 1. So max so far remains unchanged. Now check 1 is equal to 1 because index is 1. This is true. Therefore, we have found a chunk that is 1 comma 0. Now we will increase the chunks count by 1. In iteration 3, current index is 2. The current value is 2. Now max of 1 comma 2 will be 2. So max so far will change to 2, and 2 is equal to 2 because index is 2. So we will create another chunk. Now chunk count will be increased. Now in iteration 4, the index is 3. The current value is 3, and maximum will be also 3. Now check that 3 is equal to our index. Yes. Now we will create another chunk. Now chunks count will be increased 3. In iteration 5, the current index is 4. The value is 4. We will update the maximum, and we'll check that our maximum is equal to our index. Yes, that is true. We will create another chunk, and chunks count will be increased to 4. The traversal is complete. We will return 4. Let's understand why the algorithm always produces correct answer. Suppose we are at index I, and the maximum value seen from index 0 to index I is also I. The prefix contains I plus 1 distinct values because its maximum value is I. Every value in the prefix lies in the range 0 to I. There are exactly I plus 1 distinct integers in this range. Since the prefix also contains I plus 1 distinct values, it must contain every integer from 0 to I exactly once. Therefore, after sorting this prefix, it becomes 0, 1, 2, 3, and so on till I. These are exactly the values required at indices 0 through I. So the prefix can safely be separated from the rest of the array. Every time this condition becomes true, we create a chunk immediately. This creates the maximum possible number of chunks because combining two valid neighboring chunks would only decrease the total number of chunks. Therefore, the algorithm is correct. The time complexity, let's discuss. We traverse the array exactly once. For every element, we only update the maximum and perform one comparison. Therefore, the time complexity will be big O of n. And space complexity, we have used only two additional variables, that is chunks and max. So far we do not use any additional array or data structures, therefore the space will be big O of 1. Let's run this solution once. Okay, let's discuss a few common mistakes. First mistake, checking whether index of array is equal to index. Some people may think that a chunk should end whenever the current element is already at its correct position, but that is not correct. Consider that array is a 1 comma 0. At index 1 the value is 0, so first element of the array is not equal to 1. However, the complete array can form one valid chunk. After sorting, after sorting 1 comma 0 we get 0 comma 1. Therefore, we need to compare the maximum value to the entire prefix with the index, not just the current value. Second mistake, sorting every possible chunk. We do not need to generate every possible partition or sort every prefix. That would make the solution unnecessarily complicated and inefficient. The running maximum directly tells us whether the current prefix can form a chunk. The third mistake, forgetting the permutation condition. This solution works because the array is a permutation of numbers from 0 to n minus 1. All elements are unique and the sorted value at every index is known. If duplicates were allowed, the condition max of r is equal to index would not always be sufficient. There is another version of this problem called max chunks to make sorted 2, which allows duplicates values and requires a different approach. The fourth mistake, that resetting the maximum after creating a chunk. We do not need to reset the max so far after finding a chunk. We continue maintaining the global maximum from the beginning of the array. The comparison with the current index continues to identify the correct boundaries. Let's quickly recap the complete solution. The array is a permutation of numbers from 0 to n minus 1. Therefore, the completely sorted array will be 0, 1, 2, 3, and so on till n minus 1. While traversing the array, we maintain the maximum value seen so far. Whenever max so far is equal to current index, the current prefix contains exactly the value required for those positions. So we can end a chunk there. We count every search boundary and return the final count. The solution requires big O of n time and big O of 1 extra space. That completes our solution for LeetCode problem number 769, max chunks to make sorted. Try submitting this solution on LeetCode and test it with a few additional examples. If this explanation helped you, like this video, share it with someone learning data structures and algorithm, and subscribe to coinslive for more beginner friendly coding solutions. Thank you for watching. I will see you in the next video.